Greetings. Long time no see, everyone. Welcome back to the lecture series on Morse theory with no background. Last week we took a little break, and this week we are going to do a long recap of what we covered last time because it is important. What we covered last time. So here we are not going to make a new page. We're just gonna recycle some of the stuff that we covered last time, and then we're trying to finish off this theorem that we show over here. Let me mark this diffeomorphic to S2 theorem. Yep, this is a theorem that we are going to prove. So what does it say? Right, let's just start the recap right now. So let M be a closed surface, and suppose that there exists a Morse function f that maps from the surface to a real number with exactly two non-degenerate saddle points. Oh, sorry, critical points. Doesn't necessarily have to be a saddle, and no other critical points. Then this M is diffeomorphic to the sphere S2. What is S2? S2 is the sphere that lives in R3. So basically, let me draw a quick picture of what S2 is, just to give you guys some ideas. We've encountered it many times. So basically, the ball, right? The unit sphere that lives in okay, this is those are not orthogonal, but well, yeah. Imagine if they are x, y, and z. So the surface of this sphere, right? This is going to be S2. So it's basically a equality constraint. If you have a inequality constraint of like let's say x squared plus y squared plus z squared is smaller or equal to 1, that's like the entire unit sphere and everything within. So that's actually a disk. We call it D3, just so you know. All right. Okay, this is kind of slow. I should have used the eraser, but anyways. Right. So this is the theorem that we are trying to prove in this big section. So here we introduce the two very important concepts, diffeomorphism and homeomorphism. So before we talk about diffeomorphism, we need to talk about homeomorphism. And diffeomorphic is also very close related to diffeomorphism. So yeah, first we introduce this definition of what homeomorphism is. So homeomorphism is a map that maps from X to Y, some arbitrary spaces, and it has this one-to-one and onto relationship. Basically, it is injective and surjective. So if you have those two combined together, it's called a bijective map. So we show the example of what an injective is not, right? In this x squared example, f of x equals to x squared. And then also we need to find its inverse that maps from this target space y back to x. So basically like this, right? And this map is also going to be having the same property, right? It needs to be one-to-one and onto, which bijective, you flip it, it's still bijective. And also the two maps are continuous. Then this map H is a homeomorphism. And we call that X and Y are homeomorphic if there is a homeomorphism that exists between those two spaces. Okay, great. And then diffeomorphism is basically on top of this homeomorphism map H. We also need to make sure that those two maps are both of class C infinity, which is the smoothness that we've been talking about, right? So the two surfaces are called diffeomorphic if there is a diffeomorphism that maps from M to N between them. So the same thing, if there exists a diffeomorphic map, then those two places, M and N, are diffeomorphic to each other. Make sense? Okay, and then we are trying to prove this very long theorem, and so let's do again. We're still doing recap, and let's just quickly go through the very beginning, and let's resume from what we left off last time. So first, we know that right? We state in the very beginning that M is a closed surface, right? So what does that mean? In here, this M is closed and bounded. So basically, through Heim-Borel, we know that M is a compact space, right? So Heim-Borel, this is a very important theorem. Basically, in R3, Rn, sorry. We have a close and bounded yeah, closeness and compactness on the set means the set is a compact set. And yeah, so here we have a two-dimensional compact manifold without boundary. And with compactness and also with the continuity, those two basically screams out a very important theorem called extreme value theorem. So basically what that means is that we have a function that maps from M to R. This is the function, and M is compact. Our F, the map, is continuous. That basically means that our maximum and minimums are actually attained on this manifold. So we can actually reach our infimum and supremums, which they are replaced by maximum and minimums. If we don't have like closeness on our set slash boundedness, we may never achieve that supremum and infimum because those are like two bounds that yeah you're not necessarily achieving, but with this extreme value theorem, when you have a compact set and a continuous map, then those two values are attained. So now we can actually appoint those 2 points. Let's say there exists some 2 points, P naught and Q naught on this manifold, and they're both non-degenerate critical points. And by Morse lemma, right, we know that F can be put into a standard form. So what is that standard form? Maybe you look back into lecture 2, lecture 3, we know what the standard form is through Morse lemma. We can express this P naught and Q naught in some arbitrary um, coordinate chart, right? So small x and small y, big X and big Y. And we know that P naught is a max, so it needs to have an index 2. It needs to, the index number is the dimension number. And we can also use the Hessian here to represent it. And in the same way, for minimum, for Q naught, we have index 0. So basically our minimum, we can, yeah, also use our Hessian to express that. And then we can also use our quadratic form, aka our standard form, to express our F near those 2 points. And big A and small a are the minimum and maximum and minimum, respectively. Okay, great. So that's a quick recap. And now we're going to move on to resume our proof. So here, after we do that, let's consider let our epsilon be a small number. So as mathematicians, we like to use epsilon greater than 0 to be some very small number that is positive. We like to kind of like use that for like conversions or like Cauchy sequence, stuff like that. So yeah, let it be a small number such that epsilon is greater than 0. And denote by d p naught the set of points in a neighborhood of our p naught with this relationship. So a minus epsilon, some very small number, is going to be smaller or equal to f of p, which is also smaller or equal to a. So if we kind of visualize this object, what will it look like, right? So it's kind of like this little cap, right? It's a little disk, and P naught is right over here, right? So that's the set of points, and we denote such set as d P naught. That's a little dome that we're looking at, right? So yeah, so it's a very small neighborhood because we're using this epsilon as a very small number to like kind of stretch out a little neighborhood to like find this little dome of points, right? Okay, so here in also we're expressing this in some local coordinates, right? Because this is our little p naught, and we've said that p naught is our maximum, right? And we use the small x and small y, right? Right over here, small x and small y, right? We use those to express this local coordinates near p naught, so we're gonna use x and y to express that. Yeah, so we also we can find this corresponding inequality. All right, next page. X squared plus y squared is smaller or equal to epsilon, right? So this needs to be satisfied. And we know from this, right? Right. So basically, it's just a substitution. And yeah, again, we have this inequality on the top. And here, we know that this dome of points is diffeomorphic to a two disk, D2. Similarly, for DQ, we have a very similar inequality, which here I'm going to like skip the explanation because you guys should just use the same logic, right? And then we have x squared plus y squared. Now we use big X and big Y. And this is derived because of this, right? And it is also diffeomorphic to the two disk, D2. Right, so this little bowl shape, right? We have a top bowl and a bottom bowl, right? So here we have a top bowl that looks like this, and if you picture the other one, let me just draw it real quick. The other one will kind of look like this, right? So here we have Q naught. So, right, this is Q D Q naught. So we have two bowl looking things, and those are diffeomorphic to D2 because those are bowls, and bowls are diffeomorphic to two disk. I don't think I need to like show a very rigorous proof. This should be kind of you can take it for granted. If you really want to prove it, feel free. Um, but yeah, this is gonna be a little bit boring if I cover it. But yeah, if you don't believe me, search it up. But right now, take it for granted. A disk is a yeah, it's basically a bowl slash a dome looking thing. And yeah, let's move on. Here we basically have two little neighborhoods that are diffeomorphic to a two disk. Then we want to do this. We now remove the interior of our dp naught and dq naught. So those two little disks, we want to remove the interiors from the surface M. And denote by M naught the resulting surface with boundary. So what will it look like here? Let's draw this real quick. So after we remove those two domes, the interior, right? What's going to happen is that we're going to have something that looks like this. So here we took the dome off and we have some, oops, didn't mean to draw that. We have some, yeah, maybe some weird looking contour here. And here we have this. And here, let's see, we may have a contour that looks like this. And another one, another cap. Well, this is a bowl, right? Another bowl that's being cut. And we denote this as C naught and this C Q naught and this as C of P naught. So this entire thing is our M naught, right? We said we're going to denote our new surface with boundary, like such. Great. All right. Next, we're going to do some very interesting thing, but let's keep going with our description. So yeah, the boundary of M naught has boundary circles, right? That's why we use the word letter C here. So here, this part, right? I'm going to highlight it here and this little part. Those two are our C P naught and C Q naught of our D P naught and D Q naught, right? So those are the leftover boundary that after we took our cap off, we have these right, or these little circles to basically like right basically if you like think about cutting like a piece of turnip or a piece of carrot, piece of well, a big potato. So after you chop a part off, you will leave a well, like a section, right? Like a little circle shape if you look from the top from where you cut it, and that part is the boundary. And we want to denote this boundary part. Conventionally, we want to do this. We want to say that the boundary is called del M naught. So this is basically the union of our CP naught and CQ naught, right? So we have two parts, two circles. That basically forms the boundary of our manifold. After we cut those two caps, we had a manifold that's closed, and now we have a manifold with boundary, right? So we had a closed surface, and we couldn't really find what the boundary was. Now we basically cut two parts off, like little small discs, right? Little small cap, little bowls off of our entire manifold. Now we create those little circles. Okay. And we also want to denote the interior of M. This is the interior of our manifold. I'm not. And this can also be denoted as I'm not. Well, this is kind of like a set minus, but I'm just going to write minus, right? So the set of M minus the set of the boundary. That is going to be our interior, which in a way we are basically calling that, oh, that's our open set because like we are excluding our boundary, right? So here we also have a function that maps from this M naught to R, which takes constant values. Interesting, right? We have A minus our epsilon and big A minus epsilon and small a plus epsilon. So after removing the two critical points, right, we don't have any critical points now. And what are all these things leading to? Well, we're going to insert a little lemma that we're going to take for granted again. It will take quite a bit time to prove, but it's a very powerful lemma. This lemma is very interesting. So we have a function that maps from this to that, be some smooth function, C infinity, which takes constant values on boundary circles. So this is kind of what we had in the beginning here. We have this function that takes constant values, which can map to those two values. So basically on this boundary that we were looking at, the boundary circles, right? So this is the lemma that corresponds to that particular property we were looking at for our function. So yeah, so this function takes constant values on boundary circles C P naught and CQ naught. Yeah, as we can see, that's also right. Like they all should be the same values on the same level. And we assume F has no critical points on M naught, which we just showed that because we removed the two critical points, now we don't have any critical points. Then M naught is diffeomorphic to the direct product of one of the boundary circles and the unit interval. So we can also express this as CQ naught direct product slash Cartesian product with this unit interval, which kind of just looks like this thing, right? Like a cylinder in a way, right? So kind of like this little circle, right? And then direct product with this, but also just the shell of that. So basically, here, CQ naught is diffeomorphic to this boundary, which we can also, well, um, yeah, say that it's S1. So it's a circle, right? And also, M naught, this basically implies that, right? M naught is diffeomorphic to S1 because all these maps can kind of commute, right? that makes sense, right? We have a map that maps from one space to another and a space back to that. Okay, great. We're almost there, heading there. It's a long proof and it is kind of abstract, and I'm skipping a lot of the I guess arduous details, but I do encourage you to look at it rigorously, but also like I'm trying to get it, trying to show you more visualizations and try to give you more intuition so that you can enjoy more and actually maybe appreciate this subject matter. And yeah, also, I know that it's really difficult to make this, I guess, like fun, because like it is like sort of like a lecture. And I will try to find more ways, like keep you guys more engaged in this lecture. Maybe putting more memes slash like, yeah, just more visualizations, and also make sure that they are educational, right? Okay, great. Next, let's move on. So, in general, well, why do we do all this, right? So, in general, a surface diffeomorphic to this S1 direct product with 0, 1 is called an annulus. So, like a ring, right? So, excuse me, kind of like removing, so remove from the disk the interior of a small concentric disk. So something that looks like this. So this is what we're looking at, the shaded area. So is this contradictory with this shell that we were talking about with these with this cylinder? Not exactly. So imagine if you have this uh, cylinder. Maybe let's make this a little bit wider here. So we're just looking at this outside air, this shell, right? Like the surface of it. Now, what we're gonna do is that we're gonna crush it. Let me make an angry face, like some monster is trying to crush it. And after we crush this, if you think about a yeah, this thing as like a 3D object, and then you crush this surface onto a plane, right? Like a plane that this circle is living on, right? So that should just be a plane. And this becomes a analyst, right? So you're allowed to do certain things like this to basically still preserve its topological properties. They are still the same object in a topological sense because they are they basically you can reverse this and do basically do there exists a map that you can map back and forth, right? This is also a homotopy, I believe. Okay, anyways, let's move on. So here we know that M naught is an analyst based on our lemma, right? And no, why did I do that? Sorry about that. And now we can set our N naught equals to M naught union with one of our caps that we just took off. So recall our Q naught. What is our Q naught? Q naught is our minimum, right? So let's see. Yeah, Q naught is our minimum here. Basically, we attach this back. We are trying to find the union of our one of our disks union with this manifold width boundary. And now our N naught is also diffeomorphic to the disk. Oops. So we now obtain a disk, and we can paste our cap, along the boundary of our end knot to recover, oops, to recover our original manifold, M. And M is diffeomorphic to S2. How does that work, right? So before we had our little top here, right? So this D P naught looked like this little upside down bowl looking thing, right? It's kind of like a dome. And it is diffeomorphic to the disk, right? D2. So basically, we find this relationship, right? We basically get a disk. And the other one, right? So the other one is N2, right? So N2, we have this little part, this kind of glued on this weird looking manifold, right? That was too ugly, sorry. So we have a this little part that's not basically we had this chopped off, right? And there's something that maybe looks like this, right? So we know that this thing is also diffeomorphic to another D2, right? So if we add those two together, what do we get? We know that those two circles have boundaries here, and they are exactly the same on their boundary. So what we can do is kind of glue them together. And then what do we get after we glue those two boundaries together? We get a sphere. And the part we glue together is this little equator that we're looking at. So this is a gluing point. I guess it's a gluing line, the set of points that agree on their values, and they are closed sets. Great. So basically, we went through all this to prove what? To prove this very important theorem in the very beginning from the last lecture, right? That we stated in the beginning. If we have a manifold, M, that is a closed surface, which also means is a compact set. And suppose that there is a Morse function, f, that maps from the manifold to some real number with exactly two non-degenerate critical points and no other critical points, right? Then the M is diffeomorphic to the sphere S2. So our space is diffeomorphic to the unit sphere that lives in um, well R3. So basically, we can map this space back and forth to this unit sphere. Okay, and that concludes our proof. So we're going to declare victory here with a little square on the end, or some people write this. Great. So, whew, we did a lot in this lecture, and I don't want to overwhelm you guys, so I think this is a good ending point. And next lecture, we're going to start with a very short lemma and kind of prove this little lemma and then try to like kind of go over it try to introduce you guys to something called what convergence sequence is, which also is a very important concept in real analysis and a lot of optimization literature slash like research. And then we're going to talk about something called handle decomposition, which is a very interesting concept as well. And then we are going to, yeah, so let's not spoil too much. And thank you guys for listening again. If you like this lecture and like my previous lectures, please feel free to like and subscribe and give me more constructive criticisms. And I will see you guys in the next lecture.